In this video, we are going to graph this rational function by hand without using our graphing calculators or any other sort of technology. So just a reminder that this is a rational function, and to be a rational function, you need to be a polynomial divided by another polynomial. So we see this as a poly divided by a poly, and that's what makes this a rational function. And I always begin with my domain for rational functions because we usually have a domain restriction. Because remember that the denominator, in this case the x plus 5, cannot equal 0. So that denominator cannot equal 0. In this case, that tells us that x cannot equal negative 5. So our domain, written in interval notation, is all of the x values from negative infinity to negative 5, union negative 5 to infinity. And the reason why I choose interval notation for the domain rather than writing this in set builder notation, let me just show you. Set builder notation would be all values of x such that x cannot equal negative 5. This means that x can be any real number except for negative 5. But the reason why I choose interval notation is because I can see clearly that there are two intervals here, and that basically tells me that my graph is going to have two pieces. So I'm expecting to have two branches, if you will, on my graph. Next, I'm going to go ahead and see if this function will simplify at all. So I'm going to take the original function and try to factor either the numerator or the denominator or both. In this case, it looks like the numerator is going to factor. X squared minus 4x plus 4 factors into x minus 2 times x minus 2. The denominator, since it's linear, there's nothing to factor there, so that will just stay x plus 5. And then I'm actually going to rewrite the numerator, x minus 2 times x minus 2. I'm just going to write that as x minus 2 squared. So I'll rewrite that just to make that a little more succinct as the quantity x minus 2 squared. So nothing simplifies for this function, and that tells me that we do not have any holes. There would only be holes if you have a common factor in the numerator and the denominator that would cause the function to simplify. So once we find our domain and we've checked if the function will simplify, then we'll move on to our vertical asymptotes, which are going to be the values that cause that denominator again to equal 0. So the denominator will equal 0 when x is equal to negative 5. So x equals negative 5 ends up being a vertical asymptote. And I like my students to graph as they go rather than trying to find everything and then put the graph together at the end. I think we get a lot of insight if we graph as we find each piece. So I'm going to take a red pen. I recommend a highlighter or a different color for your asymptotes. Remember, it's that imaginary line that's going to be a guideline for our graph, and that's x equals negative 5. So once we find the vertical asymptotes, then we want to determine if we have a horizontal asymptote or perhaps if we have a slant asymptote. And that's going to depend on the degree of the numerator compared with the degree of the denominator. So my numerator has an x squared term, so the largest exponent is a 2, so that's degree 2. And my denominator is x to the first power, so that's degree 1. So in this case, we have basically degree 2 in the numerator, we have degree 1 in the denominator, so the degree of the numerator is larger than the degree of the denominator. And so that tells us that we do not have a horizontal asymptote. Now let me remind you why that is. The horizontal asymptote is impacting the far ends of the graph, the far right and the far left. So we're basically trying to figure out what's happening as x approaches infinity, as x becomes a really, really, really large number. And as we look at this g of x function, if it has an x squared minus 4x plus 4 on top, but on the bottom it only has an x plus 5, and you're thinking if x is really a very, very big number, letting x go to infinity, imagine if x were 100 or even x were 1,000. If we take a large number and we square it, we get a much larger number compared with the denominator that will just be x. So the numerator will always be much bigger a much larger number. As x becomes a very big number, the numerator is going to be a much larger number compared to the denominator. And that means that this graph is not going to level off and have a horizontal asymptote. So anytime the degree on top is bigger than the degree on the bottom, there will not be a horizontal asymptote. And in this case, because the degree of the numerator is 1 greater than the degree of the denominator, that means we have a slant asymptote. And some people refer to these as oblique asymptotes. So whether you call it a slant asymptote or an oblique asymptote, those words are interchangeable. And this is only going to happen when the degree of the numerator is 1 greater than the degree of the denominator. So to find the equation for the slant asymptote, we want to actually do the division in the original function. So we're going to divide the x plus 5 into the x squared minus 4x plus 4. And we can choose to do this with long division, or if you notice that the divisor, x plus 5, is linear, then you could also opt to do synthetic division. I will always opt for synthetic division given the choice because I find it more efficient. So for synthetic division, you are going to take that divisor and set it equal to 0. You're basically finding the 0 of the divisor, which is going to be -5. And that will be the value that goes in the box, essentially, for your synthetic division. And then we just take the coefficients of the numerator, the x squared minus 4x plus 4. So we have a 1x squared, so 1 is my coefficient. And then -4 is the coefficient of the second term. And then my constant is a +4. And we will go ahead and do synthetic division here. So we bring down the first term, the 1. We multiply by the value in the box. So 1 times -5 is -5. Then you add straight down to get -9. Multiply by the value in the box. -9 times -5 is +45. Add straight down to get 49. Now remember, the remainder is 49. And in this case, if we were looking at the actual answer here, my quotient, since we were dividing an x term into an x squared term, then my result would be x to the first power. So this 1 represents basically a 1x, and then -9. And then our remainder, typically you would write your remainder, which is 49, divided by the divisor, which is x plus 5. But when we're using synthetic division to find the equation for the slant asymptote, again, this is an asymptote that's going to impact the far ends of the graph as x gets really, really big, as x approaches infinity. And as x gets very, very large, then 49 divided by x plus 5, if x is a really, really big number, then 49 divided by x plus 5 is going to be a very, very small number approaching 0. And that's why many people just say you get to ignore the remainder when you're doing synthetic division to find the equation for the slant asymptote. The remainder is not needed because it becomes so very, very small as x becomes a very, very large number. So x minus 9 here gives us essentially the equation for the slant asymptote. So our slant asymptote would be the line y equals x minus 9. So next, let's go ahead and graph that slant asymptote. So it's a line, y equals x minus 9. The y-intercept is -9, and the slope is 1. So we'd go up 1 and right 1. And if you continued doing that, you would end up with an x-intercept of +9. So I can see the right-hand part of my slant asymptote here. But I do want to go ahead and continue this to the left as well. And I'm realizing that the grid I had here for this example isn't quite large enough. So I'm just going to go ahead and manually extend this. This is the beauty of being on graph paper. You always want to try to graph on graph paper for accuracy. So I'm going to go ahead and make my vertical asymptote go a little bit farther down. You might have to adjust yours as well. And just take that highlighter and extend it down, because then this slant asymptote will extend down as well and intersect eventually with the vertical asymptote. Now, there is always the possibility that the graph might intersect with that slant asymptote, so it's a good idea to check that. Therefore, next, let's answer that question. Will g of x intersect its slant asymptote? So the equation for the slant asymptote is y equals x minus 9, and we're just interested in seeing if this line, y equals x minus 9, ever intersects our curve. So we're essentially going to just substitute x minus 9 in for y on our g of x function. So we have g of x, the original curve, is equal to x squared minus 4x plus 4 divided by x plus 5. And then we're going to go ahead and take the equation for that slant asymptote, y equals x minus 9, and we're essentially substituting that in for y to see if these curves intersect. So that gives us the equation x minus 9 is equal to x squared minus 4x plus 4 divided by x plus 5. That's going to allow us to see if the function ever crosses or intersects its slant asymptote. So we need to solve this equation, and we will undo our division by multiplying both sides by x plus 5. So on the left and the right, we multiply both by x plus 5, which will require us to distribute here on the right-hand side. So we'll end up with x squared. We have negative 9x plus 5x, which is minus 4x. And then positive 5 times negative 9 is negative 45. And that's equal to x squared minus 4x plus 4. But then notice what happens when you subtract x squared from both sides to try to get the x squareds on the same side. You'll notice that the x squareds completely subtract out. And if you add the 4x to both sides to get the x's on the same side, the same thing happens. Both of those terms subtract out. So you're left with the statement negative 45 is equal to positive 4. So that is definitely a false statement. That is not true. Which means that we didn't get an answer or a solution to this equation. We didn't get an answer for x. And that tells us that this function will never intersect its slant asymptote. Now, if we had solved this equation and we had obtained an answer, then that would be where the graph intersects the slant asymptote. So for example, if we had gotten a solution of x equals 3, then we would know at x equals 3, that's going to be where the slant asymptote and the function intersect. In this case, we didn't get an answer, so no, the function will never intersect its slant asymptote. So finally, I know it seems like a never-ending process, but we'll end with getting the intercepts. So the x-intercept, or x-intercepts, will always be found by letting y equal 0. So we have 0 is equal to, now the original function, you could have the x squared minus 4x plus 4, all divided by x plus 5. Or if you look ahead, it would be actually a bit smarter for us to use the factored form. Since we've already factored it, we had it factored in x squared minus 2 the quantity squared over x plus 5. That would be smarter, save us some time, because when we multiply both sides by x plus 5, we notice that on the left, x plus 5 times 0 is just 0. So we really only end up with the numerator equal to 0. Now remember, when we have x minus 2, the quantity squared, that's really x minus 2 times another x minus 2. So when you're setting both of those quantities equal to 0, you're going to get this solution 2 times. Another way of looking at it, if you were going to undo the quantity squared, you would square root both sides. That's certainly another algebraic way of solving, which would give us 0 is equal to x minus 2, so x is equal to 2. But I like to remember that x minus 2, the quantity squared, is really x minus 2 times itself, because that helps me realize that when I solve this equation, I'm really getting the answer of x equals 2 twice, which means I have a multiplicity here. My x-intercept will be the coordinate 2, 0, but we have a multiplicity of 2. And since we've already studied polynomial functions, we've learned about multiplicities, so we can draw on that knowledge here. And we remember, hopefully, that when you have a multiplicity that is even, a multiplicity of 2 or a 4 or a 6, that causes the graph to bounce off of the x-axis at that point. Some people call it a bounce, others call it a touch. Either one of those terms, we know that the graph is going to bounce or touch the x-axis at the coordinate 2, 0. So let's go ahead and plot that point 2, 0, going back up here to my graph. So here is the coordinate 2, 0, and the graph will touch at 2, 0. And lastly, let's get that y-intercept. And once again, when you're finding the y-intercept, you're letting x equal 0. So you're basically finding g of 0 in this case. You can use the original function, x squared minus 4x plus 4, or you can use the factored form. It's interesting for the y-intercept, I think it's easier to actually use the original here. 0 squared minus 4 times 0 plus 4 divided by 0 plus 5. And a lot of people don't even bother showing this work because it's pretty easy to do that in your head, to substitute 0 into the original function, which would be fine. So my y-intercept is going to be the coordinate 0, 4/5. And we'll go back above and we'll plot that coordinate as well. So we're basically ready to try to put all of the pieces together. It's like a big puzzle. Let's put the puzzle pieces together and hopefully we can come up with a decent graph. So we know that the graph cannot intersect the vertical asymptote. These functions will never cross through the vertical asymptote. We established that it is not going to cross its slant asymptote, and it is going to bounce off of the x-axis at the coordinate 2, 0. So that must mean that my right-hand piece is going to hug my vertical asymptote. It's got to come down. It's going to hit that y-intercept. It's going to bounce here at 2, 0, and then it's going to hug the slant asymptote. So it's kind of a U-shaped graph here on the upper right-hand corner. However, if you look at your domain, we know that the graph cannot be just this one piece because the domain has 2 parts. So for example, we have established there's a piece from -5 to infinity. That's what we just graphed here. This piece, this branch, is from -5 to infinity, but we have not included the branch that's from -infinity to -5. So that means there must be another piece to this graph, and we basically have 2 options. Now don't copy this down, but just let me draw it because I'm going to erase it. We have 2 options. We could have a piece of the graph that comes from above here, hugs that vertical asymptote, and then hugs the slant like so. Or we could have a little piece down here in this kind of little V that hugs the slant and hugs the vertical asymptote. So those are the 2 options for where the 2 pieces might be. Now, we can't have both of these pieces because remember, it would not pass the vertical line test and it wouldn't be a function. So it can't be both of these pieces. So we can use a little bit of deductive reasoning here to figure out which piece is correct because we found the x-intercept already. The only x-intercept was right here at 2, 0. And if the graph was up here, when I'm graphing in green, it would intersect the x-axis again, and that would cause another x-intercept. So that tells us that we cannot have a branch. I'm going to go ahead and erase it. I cannot have this branch here because I do not have any additional x-intercepts. Therefore, the other branch of the graph, it must be down here, kind of in this little V area. So I like to use my kind of deductive reasoning there to understand where the other part of the graph must be, where it must live, I call it. Now, if you wanted to, and if you're using a computer program to graph these, for example, on Alex for your homework, if you're using a program like Alex or My Math Lab, you often need to actually graph a coordinate. So since the vertical asymptote was x equals -5, then I would go ahead and substitute in -6 into the function, and we would sub in -6 and actually get a coordinate. So imagine if I substitute in -6 into the original function. Here, it would actually be easier to use the factored form, which was x minus 2, the quantity squared, divided by x plus 5, just to make this computation easier. So we'd have -6 minus 2, the quantity squared, divided by -6 plus 5. So that's -8 squared, which is positive 64, divided by -1 gives me -64. So now I have an actual coordinate that I can plot. If I'm using an online homework system, I can plot the point -6, -64, and that would give me an actual point on the second branch. Of course, on my graph doesn't go all the way down to -64, but if you can imagine, when x equals -6, I'd be way down here somewhere, this point somewhere down there would be like -6, -64. And because that coordinate is located down here in between the slant asymptote and vertical asymptote, now I would have confidence, I would know for sure that the other branch of the graph has to live down here in this little V area. However, I prefer a little process of elimination and logic to understand that it must live down there because there are no more x-intercepts.